Some of you may already know some things about functions from the school time. In mathematics, functions are used heavily, and there is also a definition that tells you when a relation can be called a function. In algebra and other fields of mathematics, you often have to check if a function is well defined. When I was a student, no one explained to me what it means for a function to be well defined, and what exactly you have to check to find out if it is well defined. That confused me a lot. I haven't found a lot of information about this topic as well. Therefore, I have made this video. I will tell you how a function is defined and what you have to check to find out if it is well defined. We will also take a look at some examples. Okay, let's define what it means for a process to be a function. First of all, we have two sets, which we call x and y. A relation or a process f between the sets x and y, which we denote like that, f from x to y, is called a function if the relation f associates to every element x in the set capital X exactly one element y in the set capital Y. This relation f can be denoted like that. F of x is equal to y. Small x is called the input or the argument of f, and y is called the output or the value of x by the relation f. You can also use symbols to write down this definition. A relation f between the sets x and y is called a function if for every x in the set capital X there exists exactly one element y in the set capital Y, so that x is associated to y by the relation f. By the way, the set x is then called the domain of the function f, and the set y is called the codomain of the function f. So this here is the symbolic definition of a function. Let's take a look at some easy examples now. In the first example, the set x contains the numbers 1, 2, and 3. The set y contains the characters a, b, c, and d. The relation f associates elements from the set x to elements of the set y, which you can see in this picture here. The relation f is a well-defined function, because each element in x is associated to exactly one element in the set y. F of 1 is equal to a, f of 2 is equal to b, and f of 3 is equal to b2. So this relation here is a well-defined function. Let's take a look at another example. In the second example, the sets x and y are the same as in the first example, but the relation f between x and y has changed, which you can see here. This relation f is not a well-defined function. That has two reasons. The first reason is that the number 3 isn't associated to any elements in the set y. A function needs to associate each element of x to an element of y, but 3 isn't associated to any elements in the set y. So this is a reason why f is not a function. But there is another reason. The second reason is that the number 2 is associated to two elements in the set y. A function associates to every element in x exactly one element in y, and here we have two elements that are associated to 2. So f is not a well-defined function. Okay, let's take a little closer look at well-definedness now. What do you have to check to find out if a relation f between the sets x and y is a well-defined function? So, first of all, f has to be defined for every element in the set x. So, something like this here, that one element in x isn't associated to any element at all, can't happen when you have a function. Secondly, a function f only picks elements from the set x and not from outside of the set x. For example, if you have a function from the natural numbers to the natural numbers, the argument of f is always a natural number. Something like f of -1 is equal to 1 is not possible, because -1 is no natural number. Thirdly, the values f of x of the function f have to be situated in the set y and not somewhere else. So, for example, if we have a function from the natural numbers to the natural numbers again, it is not allowed that, for example, f of 1 is equal to -1, because the number -1 is outside of the codomain y, which is the natural numbers. So -1 is not a natural number. Now to the most important part. For each x in x, there exists exactly one, not 2, not 3, no, exactly one y in the set y, so that f of x is equal to y. So you have to show the following for the well-definedness of a function f. If two elements in the set x are the same, then the function values of these two elements have to be the same too. So if a is equal to b in the set x, then f of a has to be equal f of b in the set capital Y. Or in other words, if you have two representations of the same element in x, then the function values of these two representations need to be the same too. Such a situation that one element in x has two or more associated values in y cannot happen then, if this here holds true. When people are talking about the well-definedness of a function, they are often referring to this here. So if you want to check if a function is well defined, most of the time you just need to show that here. So if a is equal to b in x, then f of a is equal to f of b in y. Let's take a look at an example. The set x only contains one element, the number 4. The set y is n, the natural numbers. Now we write 4 as the sum of two other numbers s1 and s2, like that. So 4 is equal to s1 plus s2, where s1 can be the numbers 1 or 2, and s2 can be the numbers 1, 2, or 3. We have a relation f between x and y. F does the following thing. It takes a look at the numbers s1 and s2 in the representation of 4, and then it maps 4 to s1 plus 2 times s2. We want to check if f is a well-defined function. So we have to check the following thing. If a is equal to b in x, then f of a is equal to f of b too. So 4 is written as a sum of these two numbers s1 and s2. And the function value depends on the numbers s1 and s2. There are two ways to represent 4 as such a sum. The first way is a is equal to 4 is equal to 1 plus 3. 1 is the number s1 and 3 is the number s2. And the second way is b is equal to 4 is equal to 2 plus 2. 2 is the number s1 and 2 is the number s2. Apparently a is equal to b, because a is 4 and b is 4. We have to check now if fa is equal to fb. So f of a is equal to s1 plus 2 times s2. In this case, s1 is this number here and s2 is that number here. So we can insert for s1 and s2 and get 1 plus 2 times 3, which is 7. We do the same thing for fb. F of b is equal to s1 plus 2 times s2. And in this case, s1 is that number here and s2 is this number here. So s1 is 2 and s2 is 2, because we are looking at b now. So we can insert for s1 and s2 and get 2 plus 2 times 2, which is 6. And now we can see that f of a, which is 7, is not equal to f of b, which is 6, because 6 is not equal to 7. So therefore f of a is not equal to f of b. Therefore the relation f is not a well-defined function. Let's take a look at another example now. So we have two vector spaces v and w over a field K. We have a basis b is equal to b1 to bn of the vector space v, and n vectors x1 to xn in the vector space w. Because b is a basis, we can write down every small v in the vector space capital V as a unique linear combination of the basis vectors b1 to bn. So v is equal to s1 times b1 plus s2 times b2 and so on plus sn times bn. The s1 to sn are elements in the field K, and they are uniquely determined. Now we define a relation f between v and w the following way. F of v is equal to s1 times x1 plus s2 times x2 and so on plus sn times xn. The x1 to xn are these vectors in the space W, and the s1 to sn are the uniquely determined coefficients in the basis representation of the vector small v. We want to show that f is a well-defined function. So first of all, the function values are in the space W, because x1 to xn are vectors in the space W, and linear combinations of vectors of a vector space are inside of the vector space again. So this here is always an element of the space W. The second thing we have to show is the following. If there are two representations of the same vector in the vector space V, then the function values of these two representations have to be the same. But the basis representation of a vector V is unique. There is only one way to write down small v, by using these particular and unique coefficients s1 to sn. So when two vectors are the same, then v and w have the same basis representation. So the function values are the same too, because the function values only depend on these coefficients s1 to sn, and they are uniquely determined, and the same for both v and w, because they have the same basis representation. Therefore, the function values are the same too. So when v is equal to w, the two vectors have the same basis representation, and therefore f of v is equal to f of w. That means the relation f is a well-defined function. If you want to know more about this function f, or the basis representation of vectors, you can watch my videos about the linear extension principle and the basis representation of vectors. I will link them here at this point. I hope you know now what you have to do to check if a relation is a well-defined function. As I have already told you, this here will be the most important thing most of the time, showing that if there are two representations of the same element in X, then the function values are the same too. If you liked this video, please consider subscribing to my channel. It would help and motivate me to keep creating videos.